Hi everybody, so in class on Thursday or Friday, February 25th or 26th, we talked about special right triangles, and in class we talked about 30, 60, 90 right triangles in relationship, and the fact that since this is based off cutting an equilateral triangle in half, the shortest leg is half of the hypotenuse, or the hypotenuse is double the shortest leg, whichever way is easier for you to think about it. And then when we do the Pythagorean theorem, we find out that the third side is always x times the square root of 3, the short leg times the square root of 3. Okay, so we're going to learn about a different kind of special right triangle today in this video. So Darren wonders if he can discover a pattern in another special right triangle, shown at the right. Use what you know about this triangle to help Darren determine the lengths and sides of A and B without a trig tool or a calculator. So the first thing I'm going to do is just take a look. It's got an angle of 90 degrees right here and an angle of 45. And since we name things based on their angles, in the last one, let's see what this angle is. So calculators are fun for that. So clear that out. Let's see, we've got 180, whoa, blurry, minus 90, 45, excuse me, which gives me 45. So this other angle is 45 degrees, which makes this, since these two angles are equal, that makes this isosceles. But this is an isosceles triangle, which means that A must be 1. A different color for that. So A is 1. Great. Okay. So it says I need to figure out the lengths of the sides A and B without a trig tool or calculator. So we figured out A based on the fact that it's isosceles, which means the two sides have to be the same length because the 45s are the same. Okay. So how do I find B? Well, I'm going to use the Pythagorean theorem. And it says to leave my answer in exact form because I can't use a trig tool, which means I can't use SOHCAHTOA. So when it says trig tool, it's referring to SOHCAHTOA. So we can't use that, which is too bad. So we're going to go ahead and also with trig tools, we can't be exact. It says to leave our answer exact. I mean, we get decimals all the time. So anyway, see if we can figure out B because it's Pythagorean theorem. So we know 1 squared plus 1 squared equals B squared, Pythagorean theorem. B being this side, which is the hypotenuse. So that's why it's over here being C by itself. Anyway, we get 1 plus 1 equals B squared. This is just an arrow, by the way. And so I have 2 equals B squared, which means that B equals the square root of 2. Now we've just finished the quadratic formula, and we've been doing a lot of plus or minuses with our square roots. When we're dealing with shapes, we don't need plus or minuses because the shape means that this has to be double positive only. So in case you're wondering why we don't have a plus or minus in front. So B is the square root of 2. That was not hard. Cool. So that's it. That wasn't bad. So what should Darren name his triangle? And so based on the way we named the last one, we're going to call this one 45, 45, 90 triangle. Or you can call it an isosceles right triangle. It's referred to as both equally. I'm not quite the right triangle. I'm just going to put that symbol down. And so now we want to figure out if all triangles with angle, the reason we use angles, by the way, are similar. And so if we recall from our similarity stuff at the start of the year, triangles are similar if they have 2 angles that are the same measure. And so all 45, 45, 90 triangles have 3 angles that are the same measure. So yeah, they're all similar. Yes, because of AA similarity, 2 angles, all 3 angles, will be congruent. So the triangles will be similar. not congruent, similar, meaning that we change sizes. So let's go back here. I made some judgments. I should talk about these first. What do we know about the sides of an isosceles triangle? Two sides, at least two sides. Are congruent. Okay. Officially, an equilateral triangle falls in isosceles. We don't talk about it very often, but officially it has two congruent sides and therefore is here. But it's extra special, so we put it on its own. What do we know? The angles of an isosceles triangle, the base angles are equal or congruent, whichever one you want. Or in other words, the two angles at the edge of the two congruent sides, that's base angles. Or just two of the angles are congruent. Okay, whichever. Okay. All right, determine the missing side length. So here's our rule. And I know that's a little bit, we spent a lot of time developing the 30, 60, 90 rule because it's a lot more trickier. Two sides are the same. The third side is this side times the square root of 2. The hypotenuse is always the longest. These two sides are the same. And this is the square root of 2 times the square root of 2. So if we think about graph paper, I don't think I have any handy. And maybe you've tried to count the diagonal sides as 1, and you're just like, no, you can't do that. And you're like, why not? It seems like fine to me. It's not 1. So anyway, let's find the missing sides. So if this is 20, this has to be 20. That's the easy one. How do I find this side? Now, if you can't remember the rule, you can always do the Pythagorean Theorem, and I'm going to do both. The rule says it should be 20 radical 2. And I would be done faster. That's all the rule does, is it lets me get done quicker. But let's go ahead and do the Pythagorean Theorem and prove it. 20 squared plus 20 squared needs to equal my hypotenuse, which I'm going to call c squared. Okay, so 20 squared is 400 equals c squared. So that's 800 equals c squared. And so c equals the square root of 800. And this is why we were practicing simplest radical form. Okay, so the square root of 800 breaks up into 8 times 100. That's probably pretty obvious. And then 8 breaks up into 2 times 4. Okay, so I'm going to have the square root of 4, the square root of 100, and the square root of 2. And I just rewrote those. Square root of 4 is 2, the square root of 100 is 10, the square root of 2 is a decimal with my arrow. And so I ended up with 20 radical 2, and I'm finished. Now, as you can see, it's much faster to use the rule, but the Pythagorean Theorem will never let you down if you're cool with the simplest radical form piece. So I'd like you to try number 2 on your own. We're going to label this side B and this side C. So go ahead and tell me what side B is. B is 5. Good job. That one's the easy one. So now, tell me what side C is. Go ahead and pause and figure that out. All right, so C is 5 radical 2 using the rule, or 5 squared plus 5 squared, so 25 plus 25, which is 50. So 50. Now, I added two 25s together. That means I have two 25s. I could have done that here with two 400s. Two 400s, square root of 400 is 20. I could have done that. That's why it works out this way. These two numbers are always the same. So this is always double that perfect square, which is why it's always radical 2 inside. Okay? Whichever way works for you, this is the easier of the two patterns, which is why it's the one I saved for the virtual environment. I hope that, or the more virtual environment, I guess. I hope that this made sense to you, and we'll talk about it some more in class. I'll see you guys soon.